who are attending our February's research seminar. For those of you who don't know me, my name is Taran Solati. I'm the Associate in Research and Innovation in the Faculty of Forestry. Before we start, I would like to acknowledge that UBC's Point Grey campus is located on the traditional, ancestral, and unceded territory of the Musqueam people, and we are grateful to have the opportunity to study, learn, and do research on this land. I also recognize that some of you who are joining us by Zoom may be in different locations, and I also acknowledge the owners of those lands. Before we start, I would like to thank those of you who helped a lot in arranging and organizing this research seminar. I would like to thank Michelle Zhang, Frederick, and Louise for setting up the AV system, taking care of all the registration and Zoom connection. Sonia and Jillian for advertising the seminar and also the poster by Pablo, Karen and Nicole for ordering lunch and setting up the rooms. Now, I'm pleased to introduce our speaker today, Dr. Felix Wiesner. Felix is an expert in fire safety engineering with a focus on the fire performance of timber buildings and infrastructure. He has extensive experience in large-scale compartment fire tests to assess the fire dynamics in engineered timber buildings and their structural response. His research interests also consider the role of fire safety within the context of durability and service life of wood products. He obtained his PhD at the University of Edinburgh, Scotland, and worked at the University of Queensland, Australia, before joining UBC. He has received different awards for his research, including the Ove Arup Foundation Award, the Sheldon Tizon Student Award from the International Association of Fire Safety Science, and he is a 4-time winner of the Golden Pine Cone Award. So, please join me in welcoming Dr. Felix Wiesner.
Thank you, Tarani, for this kind introduction. So today I'm going to talk a bit about fire safety in general, and then try to link that to timber buildings, for example, like we're in now. Before we start, just a trigger warning that some of the events we're going to talk about today concern fires of the past, and in those fires, people died or were injured. So please just be aware if you have any trauma associated with fire, then that these topics will come up. Okay. If I'm going to ask you in the room or online now, I would assume that most of you are not super worried about fire safety in your day-to-day life. You came here, you're sitting in this lecture hall, combustible ceiling and combustible structure, and still, I guess you're not overly worried, and yet fire safety is everywhere around us. No, in here we have sprinklers, we have fire doors, we have hopefully an alarm system that will tell us to get out if we need it. And yeah, so we are feeling relatively safe because fires are relatively rare events. So not only do we have these fire safety measures, there's also a relatively low likelihood of a fire happening now or this year or even within the next 5 years. And following that, fire safety is widely accepted in society. As far as I'm aware, there is currently no politician running on a platform of reducing fire safety. Of course, sometimes this might be hidden somewhere in clauses like cutting red tape or something, but generally fire safety and also the fire brigade are very widely accepted in society. And yet fire safety has been part of a major conspiracy theory. I'm sure you've heard about this when you think about 9/11 and the collapse of the World Trade Centers. There was this conspiracy theory that jet fuel can't melt steel beams. And the theory was based on the fact that the flame temperature of kerosene is about 1,000 degrees Celsius, and the melting temperature of steel is higher than that. So the argument was that, well, the fires from the fuel in the planes could not have burned hot enough to melt the structure. And yet we saw the buildings collapse. And actually, I mean, that was a popular theory in the noughties. But I did actually find this post on Facebook from just 2 years ago. So it's still going around. It's persistent. Hopefully, I don't have to tell you it's nonsense. We'll get into why that is later. But yeah, it kind of shows that while fire safety is widely accepted, it's not widely understood or often misinterpreted how it actually works. Right? And fire safety can be restrictive. This is a replica of the City of London from 1666. And for the 350th anniversary, they rebuilt that and burnt it on a ship in the Thames. And basically the consequence of that fire was that by royal proclamation of Charles II was that you couldn't build with timber anymore. So fire safety restricting the materials we can use. Obviously, with fire safety engineering, we have moved a bit away from that. But fire safety is often seen as restrictive if you want to build something, if you introduce novel technology into buildings. And because it's restrictive, it's tightly regulated, or because it's tightly regulated, it's restrictive. But often these regulations are not well quantified. Yeah. And the reason is we don't see a lot of catastrophic fires. And because fires are relatively rare events, that means often flaws in fire safety make it into the building stock and are not discovered until a fire actually breaks out. And actually what that means is, I mean, it can be quite frustrating that fire safety is restrictive because I work with a lot of amazing colleagues in wood science. And for example, we have the guys working with cellulose and lignin and taking wood and making amazing new products out of it. And with fire safety, sometimes it feels that 50% of my job is architects telling architects what they cannot do. They have great ideas, but sorry, fire safety won't allow that. The other thing that means is because it's not well quantified is I can always say in grant applications like, well, maybe there's something that you haven't considered. You need to pay me research money so that I can find out what you haven't discovered. Actually, Kathleen Almond from the Fire Protection Research Foundation, who also worked as NIST, kind of summed it up when she said that we do have rare structural fire failures, but when they do happen, usually it's something that cannot have been foreseen on standard fire testing. And again, I can say that the need for research is there because look at this nice new timber building, would be a shame if something happens to it. Almost like a shakedown. On the other hand, I can always argue that, well, if you don't have a fire event, maybe you're spending too much money on fire safety. So really the key here is to move towards a better quantified fire safety. That's one of the things that's driving research. Okay. And at the same time, we said fire safety is restricting, but fire safety engineering can actually be quite enabling. I hope most of you know this building. It's the Centre Pompidou in Paris. And this would not have been possible without fire safety engineering because it sits right down in the center of Paris. And at the time, the fire resistance ratings required for a structure such as this would have been 4 hours. And one of the architectural features of this building is that all the structure is located on the outside, visible to the observer. So it's not hidden, it's shown, but you would not be able to put it there with 4 hours fire resistance requirement. And essentially what happened is that Margaret Law, who was a pioneer in fire safety research, at that point she worked for Arup, and she went to the authorities and showed like, oh, if we actually look what the external flame temperatures are, what the heat exposure to these external structures are, we can justify that with these fire safety features, we can build this building besides not achieving 4 hours fire resistance on these external structural elements. So it's really about doing research. I mean, the research shown here is from the 50s. It's her early work on ignition of wood actually, but yeah, she was a pioneer, and she really pushed the envelope of using knowledge and engineering to justify bold architectural visions. Okay. And how would that work in terms of how do we apply fire engineering to a building? Well, the fire safety strategy becomes very important. And if we look at a timeline, so time on the x-axis, on the y-axis, we have the fire size, the people evacuated, and the structural integrity of the building remaining. And if we look at a fire, it might develop like this. So initial phase, then a rapid growth and more growth, and eventually, yeah, getting to 100%, or in this graph, even beyond. And fire safety features could be sprinklers. So the first sprinkler can control the fire, and then we have a smaller fire to deal with. If that sprinkler doesn't work, maybe the second sprinkler will do it. If the sprinklers don't work, we have the fire brigade. So all of these create different fire scenarios that we can evaluate. And ultimately, when we think about life safety, eventually, as the fire develops, we'll get untenable conditions in the first room, we'll get untenable conditions in the first floor, and we'll get untenable conditions in the whole building if we don't manage to stop the fire at some point before that. And then we need to detect the fire, and we need to raise the alarm, and that gives people the opportunity to escape. So first, the people from the first floor, from the first room, need to escape that room before the conditions in that room become untenable. And the same principle applies to the floor and ultimately to the whole building. And if we satisfy all that, then everyone gets out of the building safely. And then, of course, during that escape, we need to maintain the structural integrity of the building. Eventually, if the fire keeps growing, we may see local collapse and then collapse of the whole building. There's different interpretations. Most building codes and laws actually say that structural collapse can be tolerated as long as everyone gets out and we don't have any firefighters in the building. But in reality, if you think about a high-rise building in the center of Vancouver, you don't really want that to collapse originating from a fire that started in a toaster somewhere. It's a disproportionate collapse. So really what we want is, we want our evacuation time to be smaller than the time to reach untenable conditions. We want it to be smaller than structural failure. And ideally, we want structural failure to happen never. Okay, so time to infinity. And I mean, I mentioned sprinklers there. Sprinklers are great from a fire safety engineering perspective. Statistically, they have helped to reduce death and injury and damage in a lot of fires. But if sprinklers work 100% of the time, then Stavros should dig out my contract and rip it apart, because then you don't need me. You don't need any fire safety engineering if you can rely on sprinklers 100%. But they don't. They have a failure rate, depending on who you ask, somewhere between 90 and 95%, which is still pretty good, but ideally you cannot rely on it. And sadly, that was shown just a few years ago, and 2 weeks ago, they released a coroner report. There was a fire in an SRO in Vancouver, and the sprinklers didn't work, and two of the occupants died. And so fire safety relies on sprinklers and a lot of other things: detection, fire resistant, compartmentation, having the adequate egress paths, and all of these things are combined, and all of these things have failure rate. And the idea then is to apply the Swiss cheese model, which you may have seen during COVID. Is kind of, okay, all of our systems have a point of failure, have a probability of failure. But if we make those holes small enough, and if we try to layer the cheese in a way that the holes do not align, then overall I get a probability of failure that's acceptable. And so the idea is kind of, okay, I have my first line of defense is maybe just the sprinklers. If they fail, then all the other systems will take care of it. That's the idea, and we'll see why that doesn't always work great. So how would we, talking about fire safety engineering, how would we look at that from a building point of view? Well, if we look at a room like this, a likely ignition source would be the EV equipment here. And if the fire starts, then hopefully at some point people will realize, okay, this is not like a stupid trick by the guy talking about fire. And we have 3 doors here. I'm only using 2 in the simulation. And eventually, okay, the guy at the front is a bit slow. Eventually, everyone gets out. And we can see the smoke descending. But in this case, no one was really affected by smoke. So everyone got out before the conditions became untenable. And if we wait a bit, I did try to simulate the ceiling as well to be made of timber. Eventually, we'll see that that timber ceiling will ignite. And so that's happening now. And that means we now have flashover. So now everything in this room is burning. And that also means flame can spread outside and can spread through the building. And yeah, I mean, I made this video to have some nice pictures to show. I didn't want to go too detailed because it can take quite a while. But ideally, at this point, we're all in the escape stairs or already outside on the fresh air. Fire service will come in if the sprinklers haven't dealt with it. And these sort of programs, I mean, this program is FDS, developed by NIST in the US. It's widely used in the fire safety industry. And it looks good because it presents nice pictures. You can put layers on there to show you temperature. You can calculate your fractional effective dose. And you can basically make sure that, okay, you separate tenants from smoke and toxicity. The problem with that is that I'm not an FDS expert. I mean, I managed to run the model, but there's so many inputs you can tweak that you can always get the result you want. Or if you put in the wrong inputs, you may get a result that's very far from reality. So there's a danger there that kind of the tools look very convincing. And I'm sure you looked at that and said like, yeah, that makes sense. But it's really about understanding the fundamentals that go behind it. And in this case, for example, it would be the ignition of the timber ceiling. I mean, I tweaked the parameters, so I did actually get ignition because I wanted to show that. But when that will happen is a more difficult question. And I have enough experience that I could look at the underlying parameters and the outputs of this model and then see whether it's actually wrong or right or how wrong I am, maybe. But the problem is that a lot of times these tools, because they work as a black box, can be abused. Okay. And I mean, this had nothing to do with FDS, slightly different topic, but we do get failure on fire safety engineering. And it's important that we learn from failure. So this is Grenfell Tower in London, in which 72 people died in 2017. And 73 people, if you count people who died a few months after later, but the official death count was 72. And it's important that we consider what happened in this case, yeah? So that we can apply that knowledge and see where's fire safety engineering going wrong, what went wrong to lead to this situation. And the first thing that's kind of striking about this that I said fires are relatively rare events, but that's only true for individual buildings. If you have a city with 1 million buildings, then actually a likelihood that any of those buildings will ignite on any given day gets closer to 1. And this is kind of illustrated also here in this building because Grenfell Tower, the fire started, I mean, it's not 100% determined, but the most likely ignition source was the fridge freezer on the 4th floor in flat 16. And that's kind of for the London Fire Brigade, that's an everyday event. In the UK, we assume there's about 2,000 white good fires per year. So if you extrapolate it to the population of London, statistically, it's literally an everyday occurrence for the London Fire Brigade. And they went there and the fire started very normally. They were very calm. It seemed like an everyday situation. But then ultimately what happened is that a lot of things in the fire safety strategy went wrong. The first of all, the building was renovated in 2012. And that meant that the cladding was combustible. And these are just some excerpts from the inquiry that show some of the thinking of the people behind it. I could spend hours talking about all the different things that went wrong. There were a lot of players in that renovation that did not act to a professional standard. But overall, it was the whole fire strategy that failed. Because in this building, what happened is people relied on that cheese theory, not explicitly, but basically everyone that was just slightly slacking in their duties to ensure fire safety relied on all the other systems working. But what happened is that the problem with this cheese theory is that it doesn't assume that those layers are dependent on each other. Because as soon as you have that vertical fire spread of the facade, you need to rethink your strategy, and you're kind of damaging the whole idea of, okay, everyone can get out. And one of the things that made this fire deadly was that it only had one staircase. And the assumption was that it can work with a stay put strategy, where basically people on the upper floors in their flats stay in their flats, and only people directly affected by the fire move out. And that put, I mean, there was a lot of criticism for the fire brigade, because they actively told people, stay in your flats, and then in the end, those people perished in the fire. So you can see that was a very difficult decision also for the fire brigade, because at some point they had to see, okay, our strategy of containing the fire to certain parts of the building has failed. But now what do we do? Because if we now change strategy, we're kind of sending people into a smoke-locked stairway. So a very difficult decision. A lot of things went wrong, from the combustible facade, fire doors not having the required fire resistance, issues with the fire escape strategy, detection and alarm, and all of these were interdependent. So it's kind of an issue with the cheese theory when we talk about fire, is that people tend to compensate. They say like, oh, we have sprinklers, so maybe we can reduce the fire resistance a bit, which sometimes works, but you need to think through the consequences of one of those systems not working, because once they become dependent on each other, all of this doesn't work. Yeah. And interestingly, I mean, Grenfell Tower was obviously a very significant event from a point of fire safety, center of London, a lot of people dying. This was a few years ago, apartment fire in the Bronx. So the investigation is from 2022, but the fire was, I think, a year earlier. And 17 people died. And in this case, actually, the people that died were the people trying to get out, and that died in the escape stair, while a lot of people that stayed in their flats survived. So complete different fates based on the fire strategy and the escape strategy. And one thing, so neither this building nor Grenfell Tower were made of wood. So why am I talking about this? But they had one thing in common, and that was they were mainly inhabited by people from the lower economic spectrum. So Grenfell Tower was a lot of recent immigrants or people from a lower income bracket, and it was the same here. And unfortunately, it's true that fire safety is not equally applied across society. And this is kind of important as we build more timber buildings. At the moment, those timber buildings are kind of marketed as higher end accommodation. But I mean, these buildings are 30 to 50 years old, and they go through renovation, they go through changes in occupancy and ownership. So buildings are also evolving, and so must our consideration of the fire safety strategy. So we need to think now, okay, how are we constructing our buildings? Will fire safety still be valid when we change occupants, when we change even the occupancy, if we, for example, convert an office building to housing? Yeah. And I mean, you can look through a lot of fire safety issues from the last 2 years, and usually it affects, it disproportionately affects people from lower economic brackets. There was a fire just last year in South Africa, in Johannesburg, and I think 53 people died. And it didn't receive a lot of coverage, mainly because people said like, well, it was an informal settlement within the building, which is actually quite common in South Africa and Johannesburg. So yeah, the blame was kind of shifted on the tenants. So it's a bit of an awkward move to timber, but yeah, so all of these buildings had one thing in common. It was tall buildings. Statistically, if you look at the BC fire statistic, we have more fire deaths actually in single family homes than in tall buildings, but the consequence of a fire in a tall building can be worse. And also it's obviously related to the fact that we have relatively low density. So if you look across BC, more people do actually live in single family homes or low rises than in high rises. But with timber, what we see is that, I mean, we have the Brock Commons right there, which at one point was the tallest timber building in the world. And it has since then been exceeded in height by multiple buildings. So now it's just somewhere in the middle. So we're building more with timber, we're building taller with timber. And this is from Professor Jose Torrero from the phase 2 expert report from the inquiry after Grenfell Tower. And he kind of pointed out that, well, we implement technology like timber because it's driven by the climate crisis, but fire safety is kind of, obviously we don't implement timber for the purpose of fire safety. It's not an afterthought. People are thinking long and hard about building these taller timber buildings from fire safety, but fire safety is challenged by new technology, in this case, building taller with timber. And if we look at this graph and actually look a bit into the future, the W350, that's a building that has been announced for Tokyo, and 350 because they anticipate that it will be 350 meters tall. So there's certainly room to grow for those timber buildings. And this is what it's supposedly going to look like. I mean, we don't know yet. This is planned for the 50s. So plenty of time to do research and hopefully get things right. But if we actually look at the trajectory of those buildings, we may be getting there much earlier. Okay. And so what's the issue with building tall timber? You may recognize this. This was announced for Vancouver. I'm not sure if they're still planning to build this. But basically, often these things are justified by these quotes. I've removed whoever said this. The structure would be predominantly made out of fire-resistant wood, specifically cross-laminated timber. It's not going to burn. Okay? And this was recently in the Washington Post. In case of fire at a wooden high-rise, damage would be contained by the requisite sprinkler systems and the fire retardant coatings on the timber. Advocates say that in the event of a catastrophic fire, the thick beams would slowly char rather than combust, and that even then the timber would burn at a steady, measurable rate. Unlike steel, which melts and suddenly folds, new timber towers have all achieved the highest safety ratings. Okay, so if we have this, then again, why did the faculty and the department hire me? What's the need for me and my salary here? Well, let's start from ignition. Which is where fires start. And we often see this kind of picture to justify timber. And we have this, this torch, which according to the picture is very hot, almost 2000 degrees Celsius. And it's applied to timber and we just see charring and no burning. Okay? The problem with that is that's not a fire. That's just a demonstration, and it kind of, I mean, it's a neat demonstration. It shows the charring effect, but actually the temperature doesn't matter so much here. I mean, you can barely see the flame, so it's a very lean flame. So the emissivity of that is very low. So meaning there's very little radiation coming from that flame. It has momentum, so as it impinges on the timber, there's a lot of heat losses into the timber and to all sides. And at the same time, the Darmköhler number is really low. So the Darmköhler number is the ratio of the chemical reaction rate to the mass transfer rate. And it means that because that impinges, there isn't actually enough time for all the combustibles that are created to react. And if we compare that to a real fire exposure, we can look at that. It's an experiment that I did as part of my PhD. So we have a piece of timber exposed here to 50 kilowatts per meter squared, and you can see it ignites after 5 seconds. I'm not applying any additional torches. That's auto ignition. So it's just that heat flux. And we'll see later how 50 kilowatts per meter squared relates to a building fire that we may consider. Okay. And also, I mean, ignition is a good way to start, but it's kind of misleading because ignition is only the initiating event. Yeah. If you concentrate on the ability of mass timber to resist ignition, you're looking at the wrong thing. Because what's going to start igniting in a fire here is not going to be the timber ceiling, but electronics, maybe someone's phone is faulty. And yeah, so the picture on the top is Daisy the cow, who allegedly started the Great Fire of Chicago. But ignition risk is always there. Obviously, we take measures to minimize it by having our electronics tested and all that, or telling our kids not to play with matches. But in the end, it's always there. No, something happens, and for example, we saw with Grenfell Tower fire, could just be a fridge freezer or your dryer that you use every day. So it will happen, but blaming it on ignition is not a good fire safety strategy. You need to account for ignition, and then your building needs to be able to deal with the consequences of ignition. Okay. And what's more important for timber is actually when it burns, is that it goes out. And here we have a piece of timber, and it was burning with around 50 kilowatts per meter squared. And you can see as we move that heat flux away, the timber self-extinguishes. And that's kind of the idea of having exposed timber like that, that eventually, if we have a fire in this room, the chairs will burn, the tables will burn, anything that can burn will burn. But as that burns out, eventually the timber forms a char layer, and when the external heat flux is removed from the timber, it should self-extinguish. We took that to the test. So this is a test setup that we had at the University of Queensland. Well, not at the university, but on White Island together with the Queensland Fire and Rescue Services. It's a 3 by 3 by 3 meter timber compartment. We have a kerosene pan in the center of the compartment that's fed from an external tank. So it's basically an inverted toilet system, like a cistern that keeps feeding kerosene into that tank until we turn it off. And on the external face of this warehouse, we have a buoyant calorimeter. So basically we're running the smoke through here, measuring temperature and gas concentration to, in the end, measure the heat release rate of the fire. Okay, so this is how it looks on the inside, and this is kind of our kerosene system that keeps feeding kerosene into that tray, and therefore we can guarantee a constant burning rate until we turn off that fuel externally, and this way we can control the fire duration. And this is what it looks like. In this case, all the timber is encapsulated with plasterboard, and we ignite the kerosene, and it starts to burn, and you can see the smoke filling the room like we just saw in the simulation. And eventually, now the video is sped up, but eventually we kind of cause flashover, meaning all the combustibles in the room are burning. You can see combustion happening everywhere in the gas phase and externally of the compartment. And we let that run for a while, and eventually we turn off our fuel supply, which should happen any moment now. And we have the whole compartment full of instrumentation. So all the wires you see hanging around thermocouples. We have thin skin calorimeters on the walls. We have pressure probes here. Yeah, and as the fuel of the kerosene burns out, the fire goes out. We don't have to put any water on it. It's burnout, and the compartment boundaries still look good. Okay, so that's the ideal case of design. The fire service doesn't even have to intervene while the fire is ongoing, or if they're busy with other things, or if they cannot intervene because the fire is very high up, it makes their job much easier and is a layer of protection. So compartmentation, kind of boxing the fire in, forcing it to burn out. Right? These are the measurements that we took of the heat release rate. So we ran one where we just turned the fuel off after about 8 minutes, and you can see kind of the burnout heat release rate goes down. We ran one that we ran for longer, where we kind of kept the kerosene just going. And then eventually what happens is you can see here an increase in heat release rate, which is due to the encapsulation failing. So now if the encapsulation fails, we suddenly have a very different fire. And we can see that actually the internal fuel load doesn't change throughout that time. But internally, because the timber starts to become involved, we're getting higher heat release rate. Okay. So having demonstrated that we can get burnout from the kerosene fire, we wanted to see, okay, what if we actually expose some timber? Because we don't want to hide all the timber. It looks good. It's cheaper to not hide it all because plasterboard costs money and labor to implement it. So we start with having 2 surfaces exposed. And this is kind of towards the end of the fire. You'll see the camera's a bit of an awkward angle. You'll see the fuel kind of slowly burning out at the center here. That's the kerosene, but I want you to pay attention also to that wall that's exposed on the left-hand side. So that's timber burning, but you can see that slowly it's less burning. So that's the timber self-extinguishing, similar to what we saw earlier. We remove the heat flux, the timber self-extinguishes, and you can see it kind of keeps burning here where the ceiling and the wall meet, because obviously at their intersection is where you have the highest feedback between them. But ultimately, there's not enough energy to keep the fire going, and we get self-extinction. So our next question is, okay, what if we add an extra wall in there? So now we have the ceiling and 2 walls exposed. And this is kind of towards the end of that fire, as seen again through the cameras or GoPro that's suspended in water just at the entry. And you can see that the timber walls and the ceiling keep burning, and now we see this char fall off. That char fall off means we won't get self-extinction because we keep exposing new timber. Also, we're forming a smoldering layer on the bottom that adds additional heat. So eventually in this scenario, we have to add water and extinguish the fire like that. So we're relying on the fire service. And the problem with that is if the fire keeps burning and the fire service cannot intervene, then all the fire resistance I can assign to that timber doesn't matter, because I'm basically creating an infinite fire until I burn through. And then I'm in the next compartment, and then maybe on the next floor. So yeah, that's a failure of the fire safety strategy right there if I cannot guarantee self-extinction. And this is what it looks like in terms of heat release. And we can say that those 3 layers, we're kind of getting close. So we can see the orange one gives us self-extinction. That's the one where we saw in the video. But for the blue one, it just doesn't reduce slow enough. And eventually we get this steady state and we get the fall off, which then increases it again. And we can see that steady state as well. If we look into the actual timber, so we have thermocouples in the solid phase of the timber, and from those we can get the thermal gradient. And by multiplying the thermal gradient with the conductivity of the timber, we can kind of back calculate the heat flux from the char to the pyrolyzing timber. And again, we see for the one that self-extinguished, we kind of see a constant reduction. We kind of see a threshold here where we align it with the self-extinction we observed. However, here we see the fuel as after the fuel's off. Again, we see a reduction, but then a steady state. So this tells us that with those 3 layers, the heat flux will always be enough to keep pyrolyzing more fuel and to keep those timber walls burning. Okay. And so we now know that those 3 surfaces are too much. But what we also wanted to test, okay, what if we don't use kerosene, but a timber wood grip, or a wood grip like that? And that wood grip is exactly the same fuel as we used in the one that self-extinguished. And this is kind of towards the end. The wood grip has burned out and collapsed into kind of this smoldering layer, as you would say, get in a barbecue. We do start to see fall off as well. And eventually you will also see fire coming through edges in the encapsulation. So now even the encapsulated timber starts to get involved. And the reason that this doesn't work, because we saw for the kerosene we had burnout, is that it takes longer for the wood grip to burn, but also because it's a cellulosic material, it leaves that smoldering char layer on the bottom, and that smoldering char layer basically acts as another surface that keeps feeding heat to the timber and keeps it burning. And again, our fire strategy has failed. And in reality, we don't usually have either kerosene or wood grips in our buildings. It's kind of a mix. No, we have some wooden tables here, but we also have plastic chairs. So we need to understand that, okay, we have a fuel load, but also that fuel load has a burning rate, and how does that fit into our fire safety strategy? In this case, when can we look at our fire safety strategy and our fuel load and see, okay, that burns out before we get fall off, before we burn through the wall, and we get self-extinction. And yeah, basically once we expose timber, we need to guarantee that we get that self-extinction. This is what it looks like for the wood grip. So again, we're comparing the kerosene one that's self-extinguished here against the wood grip, and we can actually see that, again, we see a reduction from the wood grip, but it never gets low enough to self-extinguish. And then again, the fall off drives up the heat release again. And we kind of see also the difference here, that in the internal fuel load from the scale in the center of the compartment. Now, get the kerosene after we turn it off, drops rapidly, while the wood grip kind of burns longer. And then even then we can see that even though the mass loss now is very low, that smoldering is enough just from the radiation from it to keep it burning. Okay? So looking at all these experiments, now we're looking at the heat flux that we measure at the walls directly. And you remember how I said 50 kilowatts per meter squared that we had earlier to ignite the timber. And you can see we get far beyond that in a real compartment fire. So eventually your timber will ignite. And we can see a clear delineation between surfaces that are exposed and surfaces that are protected, which makes sense. Things that are on fire have a higher heat feedback to themselves as well. But we do see that we can design the compartment to self-extinguish, and here there's no need to apply water. All of this is without any application of water. But we do need to be careful with how much do we expose, what's our fuel load, and really what are these heat fluxes that lead to self-extinction. Because looking at the one that leads to self-extinction, if we plot the individual heat fluxes that we measured from those thin-skin calorimeters at the wall and at the ceiling, is that, or here I put 40 kilowatts per meter squared because that's what Cueva said is kind of the minimum threshold you need to achieve if you want to have a chance of self-extinction. And it works really well for the wall, even though we see over the wall it takes a longer time span to completely self-extinguish. And for the ceiling, we actually have a much higher potential threshold. We see self-extinction at around 70 kilowatts per meter squared. So also it doesn't only matter how much timber you expose, but also where it is. The ceiling is easier to self-extinguish because you generally have lower oxygen concentrations there and also stagnating flow. So there's a bunch of fire dynamics issues that kind of influence how this works. And in the end, I mean, in these compartments, we did kind of have a very small opening. If you have a larger opening, you can force self-extinction earlier. But the danger there is that people set up these demonstration tests with huge openings. They point to it and say, like, see, no problem, the timber burns, but then self-extinguishes. But we cannot extrapolate that to all buildings. Of course, we can design with certain openings in mind, but we also don't know when openings will be available. One of the big uncertainties is when will, for example, glazing fail. Really depends on your glazing system, the manufacturer, the manufacturing type. So all these things play a role. I said I was going to come back to the kerosene. So these are the temperatures that we measured in the compartments that we just saw. And we can see we get to about 1,300. Interestingly, 1,300 is also the maximum range for those thermocouples, which we broke a lot of. So probably it was even higher than that. But you remember how we said that, well, 990 is the flame temperature of kerosene. So in the kerosene fires, how can we get a higher temperature? The reason is that, well, 900, that's the flame temperature of free burning kerosene, the 990. In a real fire, in a real building, there's feedback. You have all that smoke accumulating, feeding back onto the kerosene, and really accumulating heat and enabling much hotter fires. And actually, these are some of our pressure probes that we had in the compartment, and you can see the heads are somewhat melted. So, I mean, that kind of shows you that you cannot just say like, oh, there's fuel in the compartment. If I burn it outside, it burns at this temperature. Therefore, I can extrapolate to the fire behavior inside. And it kind of shows that the whole jet fuel can't melt steel beams is silly. And also it doesn't need to melt the steel beams. It just needs to weaken them sufficiently to reduce its load-bearing capacity. Okay, fire retardants are often mentioned when it comes to making timber safer. They can certainly work, but we need, again, think, okay, what are they actually achieving? Are they helping us to slow the spread of fire? Are they helping us to increase the fire resistance? Are they possibly reducing the load-bearing capacity? They increase costs. Obviously, having to run timber through a treatment process is more expensive than just using the raw timber. Once I put fire retardants in my timber, I reduce the embodied carbon or the embodied energy on it, and also make it harder to send it to landfill later. And also, this was an interesting study that came out last year from researchers in the UK. So they took pine, fire retardant treated pine and fire retardant coated pine, and checked it at different stages of a fire. And they saw like, okay, both the coated and the fire retardant worked to kind of limit the fire spread and make sure the timber contributes less to the fire or at a later stage. But then what they saw that when you actually have a fire that's well developed, when it does then start to burn, then the toxicity that's released from that fire retardant timber, especially the fire retardant treated one, was much higher than the raw timber or the coated timber. So just because you say, okay, I'll make everything fire retardant, problem solved, you may be creating a completely different problem by creating a more toxic fire. So that's another thing to consider when we weigh off different fire safety engineering measures. Okay, just to summarize, ignition is not really the issue when we talk about mass timber. I mean, it is an issue if we have timber lining somewhere, but from a structural fire safety perspective, ignition is not the risk, but more important, we need to make sure that once we get a fire, the timber will self-extinguish. And that's dependent on how much timber do I have exposed, what's the orientation of that timber, what's the fuel type, what's the fuel load, what's the ventilation of that. The timber species can have an influence, and fires have multiple stages. Now we have a growth, fully developed stage, and a decay. We need to apply fire safety to all of these, and we need to make sure that we don't conflate certain fire safety features like timber being fire resistant, timber not being fire resistant, timber being ignition resistant to a 2000-degree flame, that we don't extrapolate that to, for example, the decay phase, where we need to get the timber to self-extinguish and where we need it to keep maintaining its load-bearing capacity. I think that's it. Thank you.
Thank you very much, Felix, for the interesting presentation. That was very informative. I think we now know more about fires and more aware of them. Are there any questions for Felix? You need to talk.
The Class A classification for fire safety, what does that entitle? What does that mean?
Which context are we talking about? Is that from the US building regulations, or?
Yes.
I probably assume you're talking about flame spread ratings then, yeah. Well, that's, like I said, that's in the US, so they have class ABC. And it's a standard test. So you basically take timber and you put it in what's called a Steiner tunnel, which is basically a long apparatus, and you have a 90 kilowatt burner at one side. You start it and you see how far the flame spreads. And depending on how far it spreads, you then apply a calculation of the area over the distance, and that gives you a rating. And the rating is kind of, it's calibrated against non-combustible, which is a rating of 0, and red oak, which is a rating of 100. And I think for Class A, you need to be up to 25 for your flame spread rating. So that will be related to making sure people get out before the fire spreads too fast. Yeah.
Hi, Felix. Yes, thanks. I'm just curious about the balance between preventing fire using the safety engineering, the sprinklers and dry walls and all that, as opposed to materials. How much one should emphasize on developing fire retardant material. Sounds like you're not a big fan of that. And can you comment on the demand for fire retardant engineered building materials?
I think it depends on the context. As a researcher, I'm not a big fan of fire retardant materials because they're not very interesting to research. Often They're proprietary, and you don't often know what's in it. So you get, the timber already. You get an NDA that says you cannot reverse engineer it to even find out what's in it. You test it in standard testing apparatus, and it will tell you, okay, this works. It reduces my heat release rate from 100 to 80, which is good. Like, it can be useful, especially for protecting against bushfires and those things. But the importance is that we don't treat it as kind of a magic potion to solve issues with flammability.
Follow-up questions like, let's say in building like this, a tall wood building where you have the mass timber have exposed, is there a need for fire coating? Has that been taken care of through sprinkling or other system?
It depends what you're targeting. So I did visit a building in Kitchener that was completely mass timber, and they had the timber ceiling exposed within the main area, and that was fine. However, they needed to have flame spread rating class A, or in Canada, you would say below 25, in the escape stairs. And the escape stairs were made of concrete. But they wanted to show, oh, this is a timber building. So what they did is they put timber veneers on top of the concrete to kind of trick people into thinking that's part of the overall structure. It's not, it was just decorative. The problem then was, then they didn't fulfill the 25 rating anymore. So then they had to put, they did put an intumescent coating over the timber veneers, which kind of fulfilled the rating again. So it depends where you are looking at. Probably in this room, there's no need to achieve that flame spread rating from an engineering point of view. But if you look at the escape stairs, there you might need it. So there's greater need for that.
Any other questions?
So based on your tests, is if I've got 2 wood walls, I'm okay. I can have 2 wood walls and a ceiling and I'm still okay. Well, he can tell me that.
Well, actually, so we not in this test series, but in a previous test series, we did do 2 walls.
Yeah.
And we didn't get self-extinction for 2 walls, but we did get it for a wall and a ceiling. So that's kind of also reflected in the results that we saw, that the ceiling is easier to get self-extinction. And we do see that now reflected in building codes, that in the newest building codes, they kind of say, okay, you can have more of the ceiling exposed as long as you don't expose too many walls.
Well, what about the floor itself? Like, I'm thinking everybody has hardwood floors these days. Could that be the worst thing to do? Because when the embers fall, it's there's lots of oxygen down there. It's cool. Everything's going to burn very nicely.
Yeah, we usually don't look at the floor because often, if you look at a timber building, that will often have some sort of concrete layering. And even if you then put a laminate of hardwood floor on, the idea is that that's very thin. So it will contribute to the fire, but it will burn out. Well, if you look at the overall timber structure, where you have a wall that's 100 millimeters or more, that will provide a lot of fuel until the fire actually breaches the compartmentation.
Okay, thank you.
Any other questions? Aye.
I've got a pretty uninformed question about flame retardants, because I just have a background idea that flame retardants were used for children's clothing in the 1970s. But then wasn't there a big scandal about the fact that they actually accelerated flame and that they are actually worse than untreated clothing?
That's possibly one piece of flame retardant, but we have a lot of flame retardants in all sorts of fabric and plastics we use. It's much easier to put flame retardants in plastics and fabric because you can apply it easier in the manufacturing process. If you think about mass timber, it gets much more difficult. There was, up until the 50s, more people died in fires from burns, and then it switched to people dying from smoke inhalation. One reason was that we used more plastics, but also the rise of fire retardants meant that we had less hot fires, so less intense fires, but more smoke being formed, and more toxic smoke being formed. But I mean, it's hard to comment on individual cases. I did have cases where I tested a fire retardant, and it did actually make things worse. Well, of course, that was like just a one-off test for a manufacturer, and we told them that, and hopefully they fixed it, or certainly they wouldn't achieve the necessary ratings with that.
I have a question myself. From the research that you do and you showed us, you do testings using simulation or even the actual burning of buildings, looking at different walls and ceiling. How close are they to reality when we want to apply the results of the research to an actual building being under fire? There are a lot of different factors that then would play in terms of what type of material we have in the room, in that building. Even we can have the wind that may affect the fire. So how do you do research to make sure that the results would actually have meanings in terms of those who want to implement your results?
Yeah, that's a really good question. And it's kind of a constant balance for fire safety engineers, because buildings are varied, and we're already running behind in the knowledge against applying the technology. So the less you know, the more safety factors you need to apply, and the more expensive the fire safety becomes. So that's one trade-off. They're kind of like, and the more you know, the more confidence you can have that something works. And we kind of saw that in the self-extinction plots, where we saw the 40 kilowatts per meter square that were measured from bench scale tests in a lab by various people that agreed on that. They work quite well on that scale. But obviously in reality, it's very hard in a building code to say your building has to achieve this heat flux, but instead the limitation is going to be like, you can expose so much timber. And that's kind of what we see in reality, that all these tests we're doing that show like, okay, you can expose a bit more ceiling than wall, is now being reflected in the building codes. I'm not sure if it's this research in particular or demonstration tests. And there's also a risk that, like I said, if you set up if I design a demonstration test and I work for a timber company and I want to sell a lot of timber, I can always set up that test in a way that I will always get self-extinction and no failure. And actually one of my biggest concerns is that a lot of these demonstrations that we do now is we're kind of trying to solve the issue of flaming self-extinction, and either we achieve that or not, but then we go home. But there's also the stage of smoldering, which I didn't really have time to fit into this presentation, and also the structural capacity. Now, while this all is going on, I need to maintain the structural capacity of that. So, and for that, I need to know what is the heat distribution in the timber, which I can kind of measure from these large scale tests, but they're super expensive. So really the small scale tests help you to kind of formulate ideas and solutions. And then once you have confidence that this will work, you apply them to a demonstration test or a large scale test, and then you can go and see, okay, this fits in the building code.
Hello, can you hear me?
There are questions online, and I think Felix will read.
Yes, we can hear you. Thank you.
Hi, Felix. Roosbe from Finland is here. So it's quite late in Finland, so I didn't catch all the your presentation. I just have one general question. Do you think, like, you know, as you might know, like you definitely know, rigid polyurethanes are being used for a lot as insulator in the buildings. Do you think we can replace them with bio-based foams, for instance, because polyurethanes, if they expose to fire, they make lots of toxic gases like hydrogen cyanide and stuff.
I'm not sure I caught all of that question. Sorry, the sound transmission here is not perfect that comes through, but I think the question was, can we replace plastics with bio-based foams? Did I get that correct?
Replacing specifically rigid polyurethanes, which are being used a lot in the buildings, with bio-based foams, because these rigid polyurethanes makes a lot of toxic gases like hydrogen cyanide if they are exposed to fire.
Yeah, I mean, it depends if those biomaterials pass the necessary testing and can be shown to not be increase the risk of fires, then yes, that's possible. But obviously that requires research and testing and talking to the regulatory authority. And yeah, I don't think it's impossible. But yeah, obviously there's a pathway to do that. Thank you.
Thank you.
Thank you, everyone, for attending the research seminar in February. Our next research seminar will be in April. In March, you will have the teaching and learning research seminar. Thank you all. Have a great afternoon. Bye.